Applications of the normal distribution. So let's find and interpret the area under a normal curve. And here we're going to use z-scores. So what is a z-score? As we know, it's a very famous formula. And the formula is each point minus the mean divided by standard deviation, which basically tells us how many standard deviations a point is from the mean. So when we take a formula like this, or when we take a normal distribution like this, the mean is always at the highest point. I'm not sure why. Maybe there's a strict proof there, but I don't know. So this is because most graphs show what the area under curve is below a certain z-score, and they'll usually truncate it using z-scores, which is quite interesting. So sorry, here we go. And these are the inflection points that's saying these are the second standard deviations and third standard deviations. So we can use the empirical rule for a general idea. But now we use the formula random variable minus mean over standard deviation, which basically tells us the same thing. If this is a distribution of random variables, so how tall someone is, and a numerical measure of that. If they're like 6 feet, we can measure how far they're away from the mean. And what's really interesting here, actually, and this is what I was surprised about, all of them have the same probabilities under the same points. So take this here, and let's say this has a mean of 2 and a standard deviation of 1, so this will be 1 and 3. The area between 1 and 2 is the same as if there was a formula here, which is 90, 45, and then we'll do some simple algebra to get 135. Here, the area under the curve will be the same here, which is quite interesting. So here it should be a little bit smaller. The height should be a little bit smaller simply because the interval is a lot bigger, I guess. So yeah, it's really interesting, and that's how you use these scores to calculate this is how you use these scores to basically give us an objective scale, because all of them share the same scale, and that's why tables are really important here, and we'll get into this a little bit later. Take these two graphs. The last one is centered around the mean, with standard deviations at the inflection points. So this is about a truncated scale. So the point they're trying to make is that we should always set the mean equal to 0. And what does that mean? Let's say we have a mean of 4 within a random variable. And we'll draw a distribution here. I'm sorry for my bad drawing, by the way. It's a little bit curly, actually. And we'll say the mean is at the center. Now, what's interesting here is if we assume a standard deviation of 2, and we do plus or minus the z-score, this will be 6, and this will be 2 as inflection points. It's a little bit messy. Let me just try to make it a little bit cleaner. 2, 4, and 6. Oh, wow, that's actually pretty clean. If you look on a table here, and a table will typically give you the probabilities and the z-score the probabilities are. So this is just going to be a huge table of probabilities. And if you read the table, the left side will give you the 10th place z-score, I believe, and the top one will give you the 100th place z-score, or whatever it is. But anyways, when you look, you're never going to find a you're never going to find 6 here. And the issue is because we want an objective scale. So instead of saying a standard deviation of 6 or a mean of 4, we can simply set the mean equal to 0. And instead of saying that the standard deviation is 2, we use z-scores. So 1 z-score and negative 1 z-score. And that makes it simply a lot easier to calculate what the probability is for your certain z-score. So if it's 1 z-score away, we can find it and extrapolate it here from an objective graph, instead of saying that it's 2 standard deviations or a standard deviation of 2 away, because no graph has a table for all standard deviations. I'm sure there are some, but um, that would be infinite possibilities, so no one does that. And it's pretty interesting how the z-scores eliminate all of that, so it's a little bit easier to understand a little bit later. But simply put, set the mean equal to 0. So here's an example here. If this is the mean, we could simply set it to 0. And we use the z-scores as the scale here, which is quite interesting because it allows us to calculate the probability under a curve for all the same ones, depending on what the z-score is. Because the standard deviation calculates how far something is relative to all the other points. So it's actually interesting how the probability is the same between all bell-shaped distribution curves under the same intervals. So finding the value of a normal random variable. So let's say we want to know the height of a 3-year-old girl at the 20th percentile. So heights of 3-year-old girls, and we have a graph here. 20th percentile would be somewhere right here, or at middle 20th percent. If we want to know the height here, we can measure this probability here, and a graph at this z-score, which 20th percentile, I'm not sure what the z-score is there actually, but we just measure the interval over here. And at the 20th percentile, it'll give you everything in below. So if they're at the 10th percentile, it includes that probability and the 0th percentile as well, because it's a range, so 0 to 20. First shade in the left of the z-score to get your desired proportion. Simply add together the mean and the product of the z-score and the standard deviation. So remember the z-score formula was random variable minus mean divided by standard deviation. That's the same as the random variables equal to the mean plus z-score times standard deviation, which is pretty interesting there actually. It's just simple algebraic manipulation, and that allows us to calculate what the random variable is, or how tall the person is at the height. So it tells you what height will give you that z-score, which is really interesting actually. So yeah. In a standard normal z-table, the value you see at a z-score gives you the area to the left of that z-score. So let's take this graph again, and let's say we only want to measure the probability of being between the 10th and 20th percentile for a 3-year-old girl. That's to simply put as px is greater than 10 or less than 20. And that's the same as measuring the probability. And let me erase the sketch a little bit here. And let's rewrite it. And sorry, we didn't use a truncated scale here. So 20 here, that's simply as measuring 20, which gives us that entire interval, and subtracting the probability of 10, which subtracts this little highlighted region right here. So this is the same as P20 minus P10. And P20 gives you from 0 to 20, and P10 gives you from 0 to 10. So that's how you do so. And that's it. So